Hello, and we're going to be doing standard 2.1, which is on the measurement of systems and the diagonalization of operators. We're going to be doing problem 2.12 out of McIntyre, which states to diagonalize the Sx and Sy operators in the spin 1 case and to find the corresponding eigenvalues and eigenvectors of them. And to mention why this is an important thing to do in quantum mechanics is because of postulate 3. And it states that the only possible result of a measurement of an observable is one of the eigenvalues of the corresponding operator for that observable. So in this case, we know that for the Sx and Sy operators, the only possible measurements that we can get when we observe these are the three eigenvalues of these operators. And this is really important to know, and it's a really nice result. So now that we have these two new operators, because we're working with a new system, we're working with the spin 1 system rather than the spin 1/2, we want to know what are the possible measurements of these. And here we're going to be finding these for the x and y directions. So first we're going to write the matrix representation of the two operators, which are given in the book. So S of x can be represented as h bar over 2 times 0, 1, 0, 1, 0, 1, 0, 1, 0, and Sy can be represented as h bar over root 2 times 0, negative I, 0, I, 0, negative I, 0, I, 0. Okay. The eigenvalues and eigenvectors of these systems are given in the book. So we just want to check that we did these correctly, and this is really good. So once we find our answers, we can check to see if they're right. And we're going to start with the S of x operator and find the characteristic polynomial, because we know that the roots of the characteristic polynomial are our eigenvalues. So we have the determinant of S of x minus lambda I is equal to 0. And then we can solve with the determinant. We get this polynomial in lambda. And when we factor, we get lambda times lambda plus h bar times lambda minus h bar. And this shows us that the three eigenvalues of the system are 0 and plus or minus h bar, which is exactly what we expected. We can also note that this generalizes to arbitrarily high spin systems. If we let our spin be s, we know the number of beams exiting the Stern-Gerlach analyzer is 2s plus 1. And this means that the upper spin and lower spin are going to be plus and minus s, and that we can have every spin in between with unit steps afterwards. So in the spin 1 case, we can have 1, 0, and negative 1. And to find the corresponding eigenvalues for this system, we can solve the equation, the eigenvalue-eigenvector equation, that is S of x times lambda I equal to lambda I as an eigenvalue times lambda I. First, we're going to consider the lambda 1 equals 0 case, and we're just going to go through the other ones. All the calculations are here, but we don't have enough time to go through all these because, as you know, diagonalization calculations are very long and tedious, and we don't want to. It's just going to be a very long video if we go through all of them, so I'm just going to do a case for both the S of x and S of y and just mention the results of the other ones. So for the first eigenvalue here, equal to 0, we have S of x minus lambda 1 times I times the ket lambda 1, that eigenstate, and we set that equal to the 0 vector. When we do this, we have this system. And we note here that everything in this matrix has a factor of h bar over root 2, so we can pull that out, divide it across, and since this is a 0 vector, it cancels out, and then we just have the system of equations 0, 1, 0, 1, 0, 1, 0, 1, 0 times the vector a1, a2, a3. And here we're just going to be doing row reduction to find the values, the solutions. And our solution here is going to be the eigenvector. So, as we expect, because this is the case for all eigenvalue-eigenvector equations, is that once we get an eigenvalue and plug it back into the characteristic polynomial, we should get some sort of linearly dependent system. And exactly in the case that since we have 3 dimensions, we should have one linearly dependent row in our row space, and we should go down to two linearly independent rows once we cancel out one of the rows. And here it's easy to see what the linearly dependent rows are. The first and third are linearly dependent, for example, so we can just cancel out the third row and then solve the system. In this case, one solution is a1 equals negative a3 and a2 equal to 0. And we can choose a1 is equal to 1 and then normalize the vector we get afterwards. by finding the normalization constant, which I did not show here. But it follows that the eigenvector is 0x, and it can be represented as 1 over root 2 times 1, 0, negative 1, which is exactly what is given in the book. So we can repeat these for lambda 2 and lambda 3 for plus and minus h bar. And if we do so, we get that 1 sub x can be represented as 1/2, 1 over root 2, 1/2. And lambda 3 can be represented as negative 1 sub x. It can be represented as 1/2, negative 1 over root 2, 1/2, which are the values that are given in the book for these three eigenstates. So now we can just do this again for the s of y operator. And to do this, we take our characteristic polynomial with this operator plugged in. We solve and we get the exact same solution, so we get the same three eigenvalues as we expected, 0 and plus or minus h bar. And to find the eigenvectors, we solve the analogous equation from above with s of y. And in this case, I'm going to do a different eigenvalue, go through that one. So I'm going to go through the lambda 1 case, but for the lambda 1 equal to 0 case, we get that 0y can be represented as 1 over root 2 times 1, 0, 1, which is as expected. And let's go through the lambda 2 equal to h bar case. So we have s of y minus lambda 2 times I times the ket lambda 2. We set this equal to the 0 vector, and we get the corresponding matrix times our eigenvector b1, b2, b3. And we can note that the second row is a linear combination of the first and third rows. This might be slightly hard to see, but if we multiply this by I over root 2 and add it to this row and multiply this by negative I over root 2 and multiply by this, all three of these are going to go to 0. And then so with that note, we know now that the 0 row is the second row is linearly dependent. Therefore, we can eliminate it and we can just solve the resulting system. And here we can note that b1 equal to negative b3 equal to 1 over root 2 b2 is a solution to this system of equations. Now we can choose b2 equal to I and then normalize this vector. And this gives us the eigenvector 1 sub y, and it can be represented as 1 over 2 I over root 2 negative 1/2. This is the exact value that we got in the book once again. And finally for lambda 3, which is an identical setup, except we choose C2 in this case to be negative I rather than the I we chose from above, and we get that the eigenstate negative 1 sub y can be represented as 1/2 negative I over root 2 negative 1/2. And at this point we now have all the eigenvalues and the matrix represented eigenvectors for each of the operators as we wanted. And this completes our desired diagonalization. And we could now take the corresponding matrices of these eigenvectors and we'll just use this now. So if we take the three eigenvectors for one of these operators, put that into a matrix, and use that as our change of base matrix, we could then find that it's similar to the diagonal matrix, and then we can get that this matrix is diagonal and find its form and all. However, we're not going to go through all of that. We don't need that. We only need the eigenvectors and eigenvalues. So that's going to bring it to an end. Thank you.